Hello students. So here we are going to continue with chapter 15 waves part 2. I hope you went through part 1 where we discussed about transverse waves and longitudinal waves. So here we are going to frame a displacement relation in a progressive wave, and that too for a transverse wave. You know very well that in a transverse wave the particles of the medium vibrate perpendicular to the direction of wave propagation. So keep that in mind, that the particles of the medium vibrate perpendicular to the direction of wave propagation. In that case, the equation of a sinusoidal traveling wave is given as yxt equal to a sine kx minus omega t plus phi. Now y stands for the perpendicular vibration of the particles of the medium. A stands for amplitude. Then kx minus omega t plus phi is the argument of the sine function. K is called the angular wave number. X shows the position of the wave. Omega is angular frequency. T is the instant of time. And phi is the phase. So when the time is fixed, if you keep time constant at t0, then the equation changes from yxt equal to a sine kx plus constant. That means omega t and phi together we keep as a constant. But at a fixed location or position, when x equal to x0, then yxt will be equal to a sine kx minus omega t. So at a fixed location, y varies sinusoidally with time. That means it follows the sine function. So the constituents of the medium execute simple harmonic motion at different locations. So when t increases, x also must increase in the positive direction to keep kx minus omega t plus phi constant. So the equation yxt equal to a sine kx minus omega t plus phi represents a sinusoidal wave traveling along the positive direction of x, that is from left to right. And yxt equal to a sine kx plus omega t plus phi represents a sinusoidal wave traveling along the negative direction of x, that is from right to left. So let us see a sinusoidal waveform, and let us see an animation of that. So you can see the periodic oscillation of a particle of the medium along the y-axis. It is undergoing simple harmonic motion, whereas the wave gets propagated forward. So one wave, that is a negative and a positive, is one cycle. We have 3 cycles altogether. And if these 3 cycles take place in 1 second, then we say the wave has a frequency of 3 Hertz. Let us observe it once again. So this is a sine wave, amplitude versus time. A crest and a trough together form one cycle. Now you have a graphic representation here. So this graph shows a harmonic wave progressing along the positive direction of x-axis for different times. Now in a wave, you know, crest is the point of maximum positive displacement and trough is the point of maximum negative displacement. Here the crest is marked by a cross, as you can see in the graph, and the motion of the cross along the x-axis, positive x-axis, shows the movement of the wave. Similarly, the dot at the left extreme shows the motion of a constituent particle of the medium at a fixed location. So the dot exhibits periodic motion or simple harmonic motion, and it completes one full oscillation by the time the cross moves by a certain distance lambda. So once again, the explanation is as follows. The graphs show plots of displacement equation for different values of time. In a wave, the crest is the point of maximum positive displacement, and a trough is the point of maximum negative displacement. Here, the crest is marked by a cross mark. The displacement of the cross mark shows the motion of the wave in the direction of positive x-axis. Similarly, the dot shows the motion of a constituent particle of the medium at a fixed location. So it is also seen that the dot moves periodically and completes one oscillation while the crest or the cross has moved by a distance lambda. And the angle corresponding to lambda will be 2 pi. Now let us look at a few definitions. What is amplitude? As you can see in the representation there, amplitude is marked as A and it is in the y-axis, perpendicular direction. So in the equation yxt equal to A sine kx minus omega t plus phi, A represents the amplitude of the wave, and the amplitude can vary from plus a to minus a when sine takes values, when the sine function takes values from plus 1 to minus 1. So A represents maximum displacement of the constituent particles of the medium from their equilibrium positions. It is called the amplitude of the wave. Now phase. What is phase? The argument of sine function, which is kx minus omega t plus phi, is called the phase of the wave. Now the phase determines the displacement of the wave at any position and at any instant of time. Here position is represented by x and instant of time is represented by t. Now suppose t equal to 0 and x equal to 0. Then yxt is a sine phi. Then phi is called the initial phase angle. What is wavelength? The minimum distance between 2 points having the same phase is called wavelength. For example, wavelength is the distance between two consecutive crests or troughs in a wave. Wavelength is denoted by lambda, and the minimum distance between two crests will be, two consecutive crests or troughs will be represented by lambda. Next, angular wave number or propagation constant is represented by k equal to 2 pi by lambda. The SI unit of k is radian per meter or RAD m inverse. Period. What is period? Now period is the time taken for an element to complete one full oscillation, for a particle of the medium to complete one full oscillation. So if you represent it minus a sine omega t and minus a sine omega t plus omega t, they will represent the same phase. They will both be in phase, and capital T represents the time after one full wave, one full oscillation. So sine function repeats itself after, it will come to the same point after every angle 2 pi. So omega t equal to 2 pi, or omega will be equal to 2 pi by period. Now omega is called the angular frequency of the wave. So its SI unit is radian per second, and nu represents frequency of the wave. Frequency is defined as the number of oscillations per second, or nu equal to 1 by t, which is equal to omega by 2 pi, and nu is measured in hertz. Now, that much for transverse waves. Next, what is the displacement function of a longitudinal wave? You know very well, in a longitudinal wave, the particles of the medium vibrate parallel to the direction of propagation of the wave. So there will not be a y-axis representation there. So the displacement function will be given by s, xt. It is a function of x and t, and it is equal to a sine kx minus omega t plus phi. So we will discuss the remaining part in the next session. Thank you, students.